All right, so for skill 5, it's very much the same kind of idea as skill 4, except now we're not dealing with an interval. So we're just going to be talking about the local max and local mins. We're not trying to find an overall max. We're just going to classify whether there's a local max, a local min, or none of the above at our critical values. So we're going to go through the same process and find our critical values. So on this graph, we'd probably find those. Three values, and then I'm gonna go over the two tests to figure out whether a critical value is a local max, a local min, or none of the above. So if you have a point on the graph, so C, F at C, which is a critical point. And when we're talking about local max and mins, there's only two options. The derivative is 0 or the derivative doesn't exist at that value, because we're not going to have an interval, so we won't have those two endpoints. So if that is a point on the graph, which is a critical point, we have two tests. So the first one is called the first derivative test. And we've already done this sort of test. We didn't call it the first derivative test, but we do this when we're curve sketching. Basically, what you do is you make then a factor table for the first derivative, and you see what the signs do. So if it switches signs from positive to negative, that's like that example up there. It's increasing, it flattens, then it decreases. That point's going to be a local max. If it does the opposite, we get a local min. So decreasing, flatten, increase in that example. There's your local min. And the other option, if f prime doesn't change signs, then we know it's neither a max or a min. And that's sort of this example. It's increasing, it flattens, but then it keeps increasing after it flattens, so that's none of the above. The ones that I drew here were all critical values where the derivative is 0, all critical points where the derivative is 0. But say, for instance, we had one of those graphs with a cusp point, so there's a point there where the derivative doesn't exist. Same test works, right? It's increasing, then it's decreasing, so that point would be a local max. And remember, that comes from something like when you have x to the 1/3 in your function, then the derivative has negative 2/3 as an exponent, so x moves to the bottom. So you can plug 0 into the original. There's a point on the graph. You can't plug 0 into the derivative, so there's no, that's where the derivative doesn't exist, but there's still a point on the graph, and it might look like one of those. That example I just came up with actually looks like that, though, where it goes vertical for a second and then keeps going. So positive derivative on either side, not a local min. If it was negative that, then positive, it would be a local max. So this test works regardless of what kind of point you're talking about, but it does have to be a point on the graph, so you have to make sure you can plug that value into the original, just not the derivative, if you're dealing with derivative not exists. So that's called the first derivative test. There's another test for that point, if you so choose. It's called the second derivative test. So same setup, we have a point on the graph, which is a critical point. This one you just plug into the second derivative. So if the second derivative at that value at C, if it's positive, you have to think, well, if it's positive, it would be concave up. If it's concave up, it would look like that. We're going to get a local min at that value. If it's negative, it's concave down. If it's concave down, it might look like that. Then you know it's going to be a local max. And then if it's exactly 0, you actually don't know what's going on. So the second derivative test doesn't always give you an answer. So the test is inconclusive. You must do the first derivative test to see. Because if there isn't, so if it's something like this one where there's no local max or local min, the second derivative will for sure come out 0. But it's possible that there is a local max and the second derivative is still 0, or there is a local min and the second derivative is still 0. So you just can't tell when the second derivative is 0, and you have to do the first derivative test in that case. So it doesn't mean it's neither. It could be anything if you get exactly 0 for the second derivative. You actually have to go back and do that first derivative test. So kind of the pros of the first derivative test are that it always works. You always get an answer. You can tell which of the 3 options it is every single time. The cons of the first derivative test is you have to have the first derivative factored and do a factor table, so that sometimes takes some time. So the nice thing about the second derivative test is you just have to plug in and get a value. You don't have to do a factor table. You can just plug in that exact value and see what's going on there. The cons of the second derivative test are, one, you have to find the second derivative, which you wouldn't necessarily have to do if you're just finding local max and mins using the first derivative test. And there's a chance that it's a waste of time and it doesn't actually work if you get 0 and you have to go back and do the first derivative test either. So I pretty much only do the second derivative test if it's going to be really, really quick to check. And if it's going to be more work to check, then I just default to the first derivative test. That's my personal preference. You can decide in each case. So we're going to do that. I've got a typo in this question that I realized the first time I recorded this without my microphone plugged in. Yeah, I did 2 in a row without my microphone plugged in. So that should be a 2x squared there. So a couple things in this function. You do not need the quotient rule if it's just x cubed over 3, because that's not there's no x in the bottom, so that's not really a rational function. That first term, you don't have to rewrite it this way. You can just write down the answer, but that first term is just 1/3 times x cubed. So you don't need a quotient rule. The 3 comes down. What's nice is it gets canceled out by the divide by 3, and you get just x squared there. And then you'll get 4x minus 21. And that one factors. It factors to x plus 7 and x minus 3. So there we go. There's our 2 potential critical values. It would be easy enough to do a factor table for this one, but this is the easiest function to show you how the second derivative test works. So I'm going to get the second derivative here. 2x plus 4. So just looking back at that line there to get that really quickly. And then we're just going to plug in -7 and get -14 plus 4, so -10. So the second derivative is negative at that critical point. It is a point because this is a polynomial. So since it's negative, concave up, we know that one's our max, local max, I should say. So there's a local max at x equals -7. If we're just finding the location, I just want the x values. I don't want the y values here. At x equals 3, the second derivative is 6, just positive 10. So there, it's concave up. We know that point's our local min. So that's how the second derivative test works. This is an example where it's easy enough to get the second derivative and easy enough to plug into it. So that's probably, this type of example is where it is kind of advantageous to use the second derivative test to sort out whether it's a local max or a local min. Okay. For this one, very similar. These last two examples are very similar to ones we did just in skill 4, so the factoring and everything should work out the same. So there's my parts. Quotient rule, f prime g minus g prime f all over g squared. So the numerator should look like that. The denominator, again, x minus 3 squared. Squared is x minus 3 to the power of 4. This is a power of 2. This is a power of 2. Oh man, I'm tired. Bear with me. Sorry. There. Does that look better? I think I got it that time. Okay. Same sort of deal. We're going to factor out the x minus 3. It's going to cancel out with one of those and make that a 3, and then we'll just deal with the rest. So we have a 2x minus 4, and one of the x minus 3's. We have minus 2, and this whole quadratic. I'm tired enough that this is a risky choice, but I'm going to try and do all of this in one go. So I'm going to get a 2x squared. It's going to cancel with this minus 2x squared, and I'm not going to get any x squared terms, so that'll be nice. I'm going to get negative 6, negative 4, so there's negative 10, and then a plus 8x, so I believe I should get negative 2x. And then for my plain old numbers, I'm going to get positive 12 and positive 8. So there's positive 20. I don't know why my brain froze on those numbers, but it did. So there we go. I like to factor out that negative 2. And I like to do it correctly and make that a negative 10. Okay, so my critical values are 3 and 10. From there, this is an example where I wouldn't bother with the second derivative test because I'd have to do another quotient rule, and then I'd have to plug in those two values, and maybe it just doesn't work at all. So here is where I would do a factor table and do my first derivative test. So I have a negative 2, and that's always negative. I have x minus 10, which is negative before 10 and positive after 10. That's why I factor out that negative 2, because it makes this very easy for the factor table. I don't have to think, if I had negative 2x plus 20, I'd have to think about where that switches signs and which signs it is. We have an x minus 3 to the power of 3, so it's an odd exponent, so it can change signs. It will be negative before 3 and positive after. And so my first derivative is negative, then positive, then negative. And what I'd see is people say that this one is a local max, which is absolutely true. There is a local max at 10. It goes from increasing to decreasing at that critical value. So there we go. What I would see people write is that there is a local min at x equals 3. And that is 100% wrong. That is not true. So there is no local min at x equals 3, because if you were paying attention in this function, x equals 3 is a vertical asymptote. So vertical asymptote, there is no point at x equals 3. The function doesn't exist there, so I can't say that there's a local min point there because there is no point. It's an asymptote. So I'm going to cross out that conclusion and write the proper conclusion, which isn't really a conclusion, but I'll point out that that's where my vertical asymptote is. So I only have a local max at x equals 10 on this function, and no other local maxes or mins. And so that's why I was very careful, it's going too far, when I stated these rules. If C, f at C is a critical point, it has to be a point on the graph before you consider doing these tests. So you have to make sure that there's actually a point there. So in the case of like a vertical asymptote, there's no point there. So we're not going to call it a max or a min point. Okay, I'm going to move on to this last example. Product rule, that's going to be f, that's going to be g, f primed g plus g prime, so the 2 is going to come down, become a 1, x minus 3, don't multiply by the derivative of what's inside, which is just 1, and then f. So we have that. I'm going to common factor, so I can common factor out an x minus 3. So there we have that. I can actually also common factor out that 2, so I might as well do that. So I'll factor out the 2 and the x minus 3, and that's what I should be left with. When you clean up that square bracket, that's what you should get. So 2x squared minus 3x minus 8. So we have x equals 3. And this second bracket there, you can check it does not factor. So once more, we're going to go to that quadratic formula. So negative b plus or minus. So I got 2.886. I'm just going to round to 2.9. And negative 1 point, I'll be consistent and round to 1 decimal place, negative 1.4. So there we have it. Again, I'm not going to go through getting the second derivative because I'd have to do another product rule. I'll just make my factor table. I also want to show you how I handle that quadratic that doesn't factor in a factor table. So I have a 2, that's always positive. I have an x minus 3, that switches at 3. Now what I'll see people do is I'll see them write this quadratic once they get their 2 answers. I'll see them write it like that and then put those brackets down here. I don't like doing that because it's wrong. Like this, if you expand, you're not going to get 2x squared. So that's not the same thing. So the quadratic formula it tells you the answers that you get from factoring, but it doesn't factor the quadratic. That quadratic doesn't factor. So since it doesn't factor, I'm going to leave it as 1 factor in my factor table. And then I'm just going to use my knowledge of grade 10 quadratics to figure out what that thing does. So what I mean by that is a quadratic that opens up. So it looks like this. it's only going to be negative between its two x-intercepts. It's going to be positive before its first one. It's going to be positive after the second one. It's only going to be negative between them. Its x-intercepts are these values that we got from the quadratic formula. So the weird decimal numbers there. It's negative between them. It's positive after them. So that's how I handle a quadratic that doesn't factor. If that was a -2 in front, then I'd know it was opening down, and I'd put a plus in the middle and negatives on the outside. So that's how I handle that. So our derivative is negative, then positive, then negative, then positive. There's no tricks on this one. There's no vertical asymptote. Any value can be plugged into that equation there. So we should get a local min at -1.4, max at 2.9, and min at 3. So those are your three options there. So with that, take a stab at the exit card. Be careful with that one. It does have a vertical asymptote, so don't get tricked by that. And then we'll take that up in class, and you can work on the practice in class.